The 6.1 lesson is going to continue our work with these graphing functions. And so we are going to be graphing quadratic functions, those things with x squareds in them. And we know that if we have an x squared thing, it's not going to be a line. So up until this point, we've been graphing things that look like this, where there's no powers on the x, and we know that those make a line. Now we're going to move into something different, and this something different is called a parabola. And those parabolas are those open up or open down U-shaped graphs, and that is what we are going to be working on. Now, one of the things we know about these open up and open down graphs is they have a line of symmetry, and that's going to be a point that we are very interested in because they're evenly distributed on both sides of that line. So if we can find that line, it makes graphing a lot easier. So let's go ahead and try to tackle this graph. So basically we can go ahead and pick whatever values we want for x, put it into this function and see what comes out, and that's our graphing point. Well, without that line of symmetry, we're kind of going in the dark. So let's just start picking some cool values. So let's start with -4. So I have -4 squared plus 3 times -4 minus 1. When you work that out, you get 3. So over here at -4, 1, 2, 3, 4, 1, 2, 3. I have positive 3. So I'm just going to kind of work my way through some graphing points because I really have no idea what this shape is like. So I'm going to pick -3, and when I put -3 in the function, I get -1. Now I see that my shape is kind of starting to go down, but to really graph this, I need to find that bottom point. Where does it dip all the way to the bottom and return back up? Because at this point it really looks like it's going downward. So at -2 it's at -3. So I'm going to keep trying. -1 squared plus 3 times -1 minus 1, that ends up being -3. And now I see that my points are changing, that somewhere in this vicinity is the bottom. So I'm going to do a couple on the upswing. 0 squared plus 3 times 0 minus 1. So at 0, it's at -1. Oops, that's the problem. I graphed this one wrong back at the start. -3. -3, -1 should have been there. You guys were all wondering about that. So fix that. Let's try one more. 1 squared plus 3 times 1 minus 1. That ends up being 3. And we see this nice curve emerging with a nice line of symmetry somewhere about there, where this distance and this distance are equal. Well, it would make our jobs a lot easier if there was a shortcut to finding those things. And this is what this is. We are going to talk about the axis of symmetry, the y-intercept, and the vertex, which really is going to go back to the axis of symmetry. These are going to be our shortcuts for graphing. So first of all, the axis of symmetry, well, let's start with y-intercept. Y-intercept is a term we've heard before, and that is where it crosses the y-axis. And that's a key point for us because that's where values switch. The cool thing here is that this is the C value. Now, what is that constant value? Just like equations of a line, quadratic functions have a standard form, and those are ax squared plus bx plus c, where the coefficients are going to give us different values. So if I rewrite this equation in descending order, what I end up with is that a equals 1, because there's a 1 here, b equals -4, because my standard form is plus and c is 2. So when it comes to the y-intercept of this graph, the y-intercept is going to be that c value, so it equals 2. So on this graph, on the y-axis, that graph is going to cross at 2. Now the other values we're interested in are these axis of symmetry, that vertical line where if we fold it in half, it matches up on both sides. And so the axis of symmetry can always be found by taking the opposite of b all over 2a. And that equals x. And remember, x equals is a vertical line. The cool thing is this also gives us the vertex x-coordinate, because it's on that vertical line. So we can figure out where the vertex is if we have the x-coordinate by substituting it into our table, and we can find the bottom. The last thing that is always true that's very cool about these is whether they open up or open down. So what happens is a positive a is an open up function, and a negative a is an open down function. So before we even start picking points and plotting, we have a lot of information to work with. So if we go back to our original up here and we want to find this axis of symmetry vertex, what we have is the following. The opposite of b, my b is negative 4, so the opposite of negative 4 all over 2 times a. So I have positive 4 over 2, which is 2. So what that is saying is that somewhere on this line right here is my vertex, and all of my points are going to be equally distributed. So if I'm being a little sneaky, if this one is 2 away, there's going to be a point 2 away here. And we can check that. This is, go back to our original, a is positive, so I know that this opens up. Okay, so I know that I'm going for some sort of an open up parabola, and I have some key points. So let's find that vertex. So if I put 2 in here, my original equation is 2 minus 4 times 2 plus 2 squared. And when I work that out, I end up with negative 2. So the bottom is right here. Let's test our cheat point over here. That was at 1, 2, 3, 4. If I let x equal 4, 2 minus 4 times 4 plus 4 squared ends up being 2, just like we thought. It'd be nice if we get a couple more points on either side. So let's put in 1. And if I put in 1, I have 2 minus 4 times 1 plus 1 squared. That ends up being negative 1. And if I put in 3, I should get negative 1 out if my math is correct. And I have 2 minus 4 times 3 plus 3 squared. And that is indeed negative 1. And so if I go and graph those, we can see that our parabola is taking shape in this direction. So having those few key features definitely makes graphing go more quickly, and you've got a little bit more idea if you're doing it right or not. There's 2 other key values that we're curious about, and so I'm going to throw up an extra screen just to talk about this. If I have a parabola and one of them is open up and one of them is open down, if you go back to our idea about range values, what can come out of, if I'm thinking about what can come out of this, there's no bounds. This goes all the way up to infinity. But there is a minimum value. The lowest value it can earn or it can take is at this vertex point. Conversely, if you think about an open down, there's a maximum value right here. And then for all of infinity, it will keep going down. So when we talk about finding the minimum and the maximum values, we're looking at the vertex points. If it is an open up, we are looking at a minimum. If it is an open down, we are looking at a maximum. And if you ever get confused, just quick sketch a picture and think logically about open up or open down. So if we go back to this example, find a maximum and minimum value. The minute I look at this function right here, this a value, a is -1, and that tells me that this is going to open down. And as soon as I know it opens down, that tells me I'm going to be looking for a max value. And so the place where I look is at the vertex. So if I'm looking for the vertex, I need to use that line of symmetry. So x is the opposite of b over 2a. Well, here b is 2 and a is -1. So I have the opposite of 2 all over 2 times -1, which is -2 over -2, which is 1. So that's the x-coordinate. When I think about the x-coordinate being 1 and I need to know what comes out of it, I substitute in -1 squared plus 2 times 1 plus 3, and this ends up being 6. And so 6 is my maximum value. If we graphed it, that is the largest value that will come out of my function. I will continue the word problem on part 2 of this video.